Hello and welcome to my presentation. I will be reviewing the paper Autonomic Computing Challenges in Fully Autonomous Precision Agriculture. I will discuss the main points of this paper, its relevancy, and give some critique as to the limitations found in the paper. This paper was published in the International Conference on Autonomic Computing in 2019. As with every process, improving efficiency by reducing costs and improving time management is vital. By reducing the operating costs and improving the efficiency of monitoring crop health via aerial observations, a farm can allow for more data collection with little to no loss in profit. It is impossible, however, to remove the cost of collecting data entirely, as there will always be a fundamental cost in operating an aerial craft and processing the images. However, this cost can and should always be driven down to improve overall efficiency. As crop fields grow larger with a high demand for food, efficiency will decrease. Thus, planning for future growth and ensuring a scalable solution is essential. This paper explored previous methods that have been used to achieve mapping of the same crop field. These methods are a piloted airplane, UAV with remote pilot, and fully autonomous aerial systems. The latter system does away with pilots entirely. Instead, it is a management system that controls flight, image capturing, and data analysis. It achieves this by connecting to a set of drones and managing them in a manner that has been programmed by an expert. The paper further discusses its opinion on fully autonomous aerial systems by linking it to fully autonomous precision agriculture. This simply means a fully autonomous aerial system that produces a yield map report. The final method that I have discussed is the most complex in terms of calculating operating costs. This is due to the introduction of necessary and costly computation. The authors of this paper saw an opportunity to implement autonomic computing into fully autonomic precision agriculture. The benefit of autonomic computing in fully autonomic precision agriculture was to reduce the computation costs while allowing for autonomic control of the drones and imaging. Reduction in hardware is also achievable through edge-to-cloud bursting. This method so far has shown improvements by reducing the required hardware and doing away with continual expert input. By using less energy and by removing the need for expert input into mapping, cost will be significantly reduced. To test this new method of imaging, a simulation was done by processing data from 7,000 cornfield images composed into 1,350 sample runs. This simulation was conducted by profiling the energy demand for an aircraft. For the software, the delay and power were measured on a laptop. Cloud offload was not used in these tests. The simulation was tested over 3 different percentages of an area. This allowed for observations of scaling. System A consisted of an accelerated FAPA system equipped with an edge device with an accelerator. System B consists of a basic FAPA system equipped with an edge system comprised of only a single CPU. System I makes use of autonomic software components that allow for policy-driven autonomy, effectively doing away with labor costs. The results of these tests are shown in the figure on the right. System A and System B both have significant increases in costs as the amount of area being mapped increases. This is a result of increasing labor costs required to control the drones or aircraft. Computational costs remain constant for each system, although System A has the largest cost. This is due to the addition of the accelerated FAPA, most considerably due to the GPU unit. The removal of labor costs is the biggest benefit of System I. This allows for significantly better scaling. While the output of the simulation does show a promising result, it is still only a simulation, and as such, needs to be field tested before more confidence can be placed in the applicability of autonomic systems being implemented into fully autonomous aerial systems. This concludes a presentation on autonomic computing challenges in fully autonomous precision agriculture. Thank you for your attention.